Hey everyone, this video is about the double pendulum, one classic example when it comes to physics. Now, we usually do it with pen and paper, where we develop all the equations, formulas, and etc. But since we have modern tools, we will be using Python to solve it and animate it with matplotlib. By the end of this video, you will be able to animate the double pendulum in Python very easily with different masses, different gravitational forces, and so on. It will be kind of a step-by-step tutorial, so if you have no idea how to do it, this video is right for you, where we will explain a bit in detail every step you need to execute in order to achieve it. I'll be dividing this video in different time steps so you can directly go back and check each section you want to check. Now, without further ado, I hope you enjoyed this video. Leave a like, subscribe, and let's go. So, solving the double pendulum problem in Python. Now, the first step, as my previous video, was to first import the essential libraries. So with this I mean we import numpy, we import odeint from the scipy don't integrate. This will be later on used to solve our differential equations, and we import sympy. So this is a symbolic, let's say, module in Python. Now here is the double pendulum problem. We have two masses m1 and m2 that are both linked with a rod, L1 and L2. Now, for the purpose of simplicity, we will consider L1 and L2 is equal to 1. It will simplify a bit all the symbols and everything. But we will consider different masses m1 and m2. Our system can be defined with x and y1 and x and y2. But since we can convert it into polar coordinates by using theta1 and theta2, so that's what we will be using right now. Here I define all the symbols and variables of my problem. We do this using the sm.symbols, and then we specify the symbols. For example, t is equal sm symbols t. If I go ahead and print out t all the way down here, print it, you see that's t. Same goes for m1, m2, and g. Doing the sm.symbols of m1 space m2 space g, and specifying they are positive constants. That's very important to do. Again, if I do like m1, it displays it correctly. Now I can also do m1 plus m2, and then let's say minus g. This is nonsense, but you can still do it. Alright. Then we define theta1 and theta2, so these one, theta1 and theta2. They will depend on t, so we define them with sm.symbols. Now, these are, quote, theta1 and theta2. This will be just in a way to tell Python to represent these variables with this type of LaTeX style. So if I go ahead and do theta1, you'll see that it displayed it. Now ignore this part right here, this of dependence of t, this will be later on. But you see that here we display it as a LaTeX style, let's say. Now we specify the class as a sm.function, since theta1 and theta2 will be two functions of time, like so. This is why we have theta1 of t. We define x1, y1, x2, and y2 with sine of theta1. So let's go back here. You see that this mass right here, the x coordinate, so if we project it right here, it will be this distance, so it will be sine of theta1, and the y coordinate, supposing our 0 or our origin is right here, our y coordinate will be this distance right here, so it will be minus cosine. And same goes for here. The coordinate of this mass right here, the coordinates are these coordinates, so x1 and x2 plus this length and this length. Again, this length is defined with minus cos theta 2, and this length is defined with sine theta 2. This is exactly what we are doing right here. So x1 is equal to sm.sine theta 1, y1 is equal to minus sm.cos theta 1, and then x2 is equal to x1 plus the same thing, and same goes for y2. So if I go ahead and print out x1, you will see that it is equal to sine of theta 1. Same goes for x2. We get this expression right here. Alright, so we've successfully defined the variables of our problem. So theta 1, theta 2, x1, x2, etc. Now, again, the first step was to import the libraries. Second was to define the symbols and variables using simpy.symbols. The third step will be to calculate the first and second derivative of theta I, so theta 1 and theta 2, which means d theta 1 dt, d theta 2 dt, and then the second derivatives of these two. Now we will also be defining the velocity across x and y. This will be later on used for the energies. We use simpy.diff, like so. Here, the first derivative of theta across t will be defined with sm.diff theta 1 and across t. Same goes for the second derivative, so it's the angular acceleration. We do it the same for x1, y1, x2, y2, and theta 2. So if I go ahead and print the first derivative of x, it's equal to cos theta 1 d theta 1 dt. Now x is a function of theta 1, which itself is a function of t. To differentiate it, you use this formula right here. And same goes for the other ones. You can also display theta 2 dd, which is the second derivative of theta, like so. And same goes for all the rest. Alright, so let me rerun this and move on. Now the next step will be to define both the kinetic and potential energy to get our Lagrangian, which is equal to T minus V. Since we have a double pendulum, so we have two masses, we are going to mention the kinetic energy of the first mass and the second mass. Now the kinetic energy is defined with half m times the velocity squared. Now the velocity is defined with the square root of Vx squared plus Vy squared. So the square root plus the squared, the outer squared will nullify, and we will get this expression right here. So we define T1 and T2, as well as V1 and V2 with M1 times G times Y1, and respectively Y2 for the V2. The Lagrangian will represent the sum of the kinetic energy minus the sum of the potential energy, like so. If you want to display the Lagrangian here, it'll be a very long expression. You do not have to do it by hand now, since we have Python plus symbolic expressions. We formulate Lagrangian's equation for a non-damped system. Since we have two masses, we have two equations for theta 1 and theta 2. Here is the first equation, and here is the second equation. We define them. Sm.diff L theta 1d, this thing right here, represents this expression right here. And then we differentiate all of this across t. So this is the first element, minus sm.diff L theta 1. And this is the second element. And same goes for the second equation. If we have terms to group or terms that nullify themselves, we can use the le1.simplify. So we are going to simplify this equation if it's necessary, but it's more or less optional. We have L1 and L2. If I go ahead and print LE1 or LE2, get this long expression right here. So remember, this, all of this expression will be equal to 0. In order to solve our problem, we want to solve both of these equations and the second derivative of theta 2. That's what you do right here. We create a function that solves Lagrange's equation numerically for the double pendulum system. sm.solve, so this one right here, we get the solutions, solves the equations L1, LE1 and LE2 for theta 1 dd and theta 2 dd respectively. So which means that we will extract theta 1 dd from this equation and theta 2 dd from this equation right here. Which means we will have an array containing these two solutions: the angular acceleration of the mass 1 and the mass 2. This is what we are doing right here, alright? And then we convert that symbolic expression into numerical functions using the sm.lambdify. So here, sm.lambdify. It will take arguments, for example, theta 1, theta 2, and then t, m1, m2, etc. If we give these values right here, it will spit out a numerical value. So let's say, for example, Right, so this represents, for example, theta 1, theta 2. Suppose we have these parameters right here. Right, so if I run this, you'll see that it spits out a numerical number. Let's say I change this to 1. You have a different value. Here, this specifies that we are mentioning the first solution, so this one, and this refers to the second solution, so theta 2 dd. Now we know what theta 1 dd and theta 2 dd are equal to. It's time to solve our system. We solve our problem numerically using odeint, the provided function of scipy.integrate. We are interested in finding the angles and angular velocities of the two masses in form of a vector y1. So y will be the vector of solutions that we are going to search for. Theta 1 dot, theta 2, and theta 2 dot. Now I'm not sure if it is actually the Range-Kuta method that is used in the odeint function, but we'll see. In numerical analysis, the Range-Kuta are a family of explicit and implicit iterative methods, which includes the Euler method used in temporal discretization for the approximate solutions of simultaneous nonlinear equations. Now think of it as the Euler method. You know how we usually approximate these first order derivative with, let's say, yn plus 1 minus yn divided by dt. Now we can express y of n plus 1 being equal to y of n plus dt times the derivative. This is also called the Euler method. Now, in other words, we have the following numerical scheme. We have theta 1 that we are seeking is equal to theta 1 previous plus dt times the derivative of theta 1. Theta 1 dot that we are searching for is equal to theta 1 previous dot plus dt times the second derivative of theta 1, and same goes for theta 2. So in other words, we have a vector y1 that we are searching. We get it by taking our previous y1 vector, we added a quantity, which is a time interval dt, times a derivative of that vector y. So this is right here. Now, odeint is a function that takes a function, the initial conditions, additional arguments, and a discrete time array. So here you can see that our solution will be equal to odeint of system of ODEs. So this function right here, I'll come back to it in a second. Our initial conditions, which are these ones. The time points, here we define it with an np.linspace from 0 all the way up to 40 seconds across 1000 points, and some additional arguments, which are the m1, m2, and the g, which will be used to compute LEF1 and LEF2. So here LEF1 represents Lagrangian equation function 1 and Lagrangian equation function 2. Alright, so let's come back to our function right here, system of ODEs. Now, it takes a vector y. So this vector is the same as this one right here. And then a time, t, m1, m2, and g. We extract from the array y theta 1 dot, theta 2, and theta 2 dot. We use then these values right here plus these ones to compute the second derivative of theta 1 and theta 2 using the LEF1 and LEF2. And then we return another array. So in a way, what we're doing, at the beginning we have initial conditions. So we have this one right here. Let's say I is equal to 0. So we have theta 1 of 0, theta 1 dot of 0, theta 2 of 0, and theta 2 dot of 0. We have these ones, which are right here. We extract them from y. Okay. The next step will be to compute dy over dt, this vector right here. So it's all of these elements right here. We already have d theta 1 dt and d theta 2 dt, which are these one, theta 1 d and theta 2 d. Now the next step is to compute the second derivative of theta 1 and the second derivative of theta 2. We compute theta 1 dd and theta 2 dd using these two lines of code. So we replace all the parameters, these ones, in our equation here. And we do the same thing for theta 2 here. And we will get theta 1 dd and theta 2 dd. We then return this array right here, which is dy over dt. And then this function odeint will automatically compute the y of I plus 1, and we will redo the same process where we will extract the angles and velocities, compute the derivatives, and then estimate the new vector y. Now solution will be in the form of, right, so now the solution we are getting will be represented in this sort of array, where this first element represents the solution for t equals 0, and then this will be for t equals t1, and then this will be for t equals t2, etc. The first element of this part right here will be theta 1, and then theta 1d, theta 2, and theta 2d. So in order to extract the solutions, we do it right here. We go across all the lines, and we take the first element. This is theta 1. We redefine x1 and y1 as well as x2 and y2 using np.sign, so it's exactly the same as the ones right here, though instead of using a symbolic function, we use a numerical function of sine and cosine. Okay, so let me print x1. You'll see that we have actually an array, so this is x1 at t equals 0, t equals t1, t equals t2, all the way up to t equals the end. Now in order to achieve the simulation you saw in the beginning of the video, I tried to make it in Jupyter Notebook, so we will be seeing what everything of this does. But you see here, it's not quite updating. This is why I made another file here. It's a regular Python file where I copied all of the code we just saw, and if I run it, you'll see that now it's working. Now we will see how we can make this animation right here and what is the logic behind it in a very simple and easy to understand way. Alright, so let's go. Alright, so this is actually the next day. Anyway, now we can see here that we have our script of the double pendulum. Right, so I will omit all of this part and we will do this together. Right, before we do that, I first want to explain to you the logic behind this very simple animation. It's very basic and can be understood with this picture right here. Now, we have a double pendulum right here. So, first mass and second mass. Let me actually change the color, like so. Now here, what is the pendulum made of? It is made of two masses and two rods, right? So here, in a way, a rod can be represented with a segment, and a mass can be represented with a dot. This is why, for example, in this picture right here, this can be a line, and then we have a dot, and then another line, and another dot. Most likely have been representing lines and dots in Matplotlib very frequently. To define such a line, for example, you will give it the coordinate 0 and then x1, followed by 0 and y1. To define this line right here. Same goes for this line. We define it with x1, x2, and then y1, y2. Since we have the solutions y1, x1, and x2, y2 right here, remember, we already got this solution. And now the mass m1 will be very easily represented with a dot, and so goes for m2. Alright, so let's actually try and do this in our Visual Studio Code interface. We start by importing Matplotlib, going to import the function, the animation function. Dot animation import func animation. Alright. Now, using this logic right here, we are first going to draw our still pendulum, so our non-moving pendulum. I will do it with a figure axis is equal to plt.subplots. By the way, I have a second screen here, so I minimize the errors for your time and my time efficiency. Okay, let me copy this and do this right here. Oh yeah, I'm silly, I forgot. Here it's from. Alright, and then we are going to add a grid. So ax or plt dot grid. Alright, add a plt dot show. Okay, if we run our code and then wait for the magic to happen, eventually you'll see that we have our plot right here. Now, first step will be to add this rod right here. So this first rod, let me actually clear all of this. We're going to define this rod by defining it 0 x1 and then 0 y1. Alright, so let me do this right here. I will call it pendulum 1 is equal to a ax.plot, and then remember you want to draw 0 x1 and 0 y1. So we do a 0 pendulum x1 of 0. We will draw the initial stage of the pendulum, so when t equals 0 we do a 0 x1 pendulum, and then for y same, just changing this, and we add a line width of 2, let's say. Alright, so let me close this and let me rerun that. Alright, very good. Now you can see that we have our first rod. We can do the exact same thing with our second rod. So I'll do this and call it pendulum 2 is equal to ax.plot, and then here it will be x1 and then x2 of 0, and then here it will be y1 and y2 of 0. Again, see, it's here x1, x2, and then y1, y2 to define this rod right here. Now again, if I want to run the code, you'll see that it will display now the both rods, like so. We have both our rods. Now we will represent both masses m1 and m2 like the following. So we have mass 1 is equal to ax.plot, right? So this will be the x and this will be the y coordinate in form of an array. Remember, this is important for the plot function. Here we have this mass right here, so it's x1 y1, here is x2 y2. Alright, so this will be x1 of pendulum 0, and this will be y1 of pendulum 0. And then the same goes for mass 2, only that here it will be x2 and here it will be y2. So we can add additional arguments to make the dots a bit more relatable. For example, let me just copy this right here, so, and paste it right here. I add a marker of O and a marker size like this, which will adapt to this one right here. These values are right here. So in a way, the more a mass weights, the bigger it will appear on the screen. So it just scales up the mass. That's it. It's really nothing fancy. I do a int times 4 plus 1. Alright. The same goes for this one. And if I run this code, you'll see that now we have pretty decent looking, simple yes, but pretty decent looking pendulum. It doesn't move. That's a bit boring. So let's make it this bad boy move. And to do so, it's actually very easy. You will define an update function, like here, called def update. And we'll pass. We will define our animation called animation is equal to func animation, passing in the figure, our update function. The frames will be equal to length to this one right here, time points with an interval of 25 is equal to 25, and blit is equal to true. So here blit will in a way optimize our plot. Intervals, so this is referring to the frames per second. Since we have here 0 to 40 seconds across 1000 points, if you do the math, you will see that between each second we have 25 elements of this array. So we want to, in order to scale the animation and make it like real time, you will need 25 frames per second. This is why this interval argument is set to 25. Alright, with a total of 1000 frames. Alright, and the update function. Now the update function, we are going to update the data of pendulum 1, mass 1, pendulum 2, and mass 2. Dot set data. Here we will pass in the frame, and then dot set data exactly the same as these ones. Okay, only that we will update it with the frame index, and then same goes for pendulum 2. This will be y2, and then this will be y1 of frame. So it's exactly the same as this one. Let me actually copy this to minimize all errors. I'll do this, call this of frame, and this. Alright, and same goes for mass 2. Mass 1 dot set data, the exact same thing right here, but instead of 0 we are going to update it with the frame index. Specify this to 2 and then 2, returning pendulum 1, mass 1, pendulum 2, and mass 2. This is it, I think, so let me run the code and see. This is what we all have been waiting for, by the way. This is why the video is so long. Alright, so I clearly... There's clearly a problem with this pendulum. Let's see. Am I passing everything correctly? Oh yeah, here it's pendulum 2. Alright, let me rerun the code. I'm so excited for this. I can see here is our beautiful bad boy dancing around. Now, this is what we all have been waiting for. This is why this video is so long, but there you go. There you have it. That's a pretty solid pendulum animation in Python. Of course, you can modify it as much as you want. For example, if you want to see the gravity on Mars, I think it's equal to 3.6 something, and then let's say one mass is equal to 2 and the other mass is equal to 10 kilograms, let's say. We run the code. Here we can see a whole other animation. Very weird animation indeed. I think I just have to modify this to M2. Here's how the pendulum will behave on Mars, for example. Very interesting, if you ask me. So we can clearly see that this mass is dominant relative to this small mass. But of course, we can go a little step further and we go back to Earth. No, it's 9, right? I totally forgot what's the value. I think it was like this. We can change the initial conditions. For example, we start with a velocity of, let's say 10, and we set another initial velocity of theta 2. We run our code, and look at this crazy boy. Now you can see you can modify these conditions as much as you want, and it will be a very chaotic system, each time resulting in a different simulation, as you can see right here. But yeah, this was my objective with this video. I hope you enjoyed it. I hope everything was clear to you. If there is some points where maybe I wasn't explaining well enough, just let me know in the comments. Now I hope to see you in the next interesting video. If you have topics or want to suggest anything, let me know. I'll be sure to check it out and maybe make a video about it. And see ya. Hey, thank you for watching this video till this point. Hope you liked it. I very much enjoy making these types of video, though a like or a subscribe will help me and motivate me tremendously. Feel free to check my other videos. I got some Python tutorials, but also some educational math. And I hope to see you on the next video, and peace!